So this talk is pretty much about Apache Apex and Apache Geode integrations, what we do. So having a good overview of what Geode is and what are the capabilities of Geode, we're going to see how those capabilities of an memory grade can work with the streaming technology and unfold a lot of new kind of feature sets which was not explored before. Okay, so first look at what is in-memory data grade. So in-memory data grades are a cluster of commodity servers which host the data in memory distributed across the servers, gives an efficient object-oriented model, object-oriented APIs to access the data, to store the data and update the live data. This features enables streaming computation framework like Apex to use this data grades to store large data, in streaming hot data into in-memory data grades like Geode, which can be accessed in a fault-tolerant manner in a very efficient latency. So this distributed in-memory data grids, which gives access to update the data in fairly less than a second. So this combined with the streaming technology gives a lot of application patterns which can work together, and this is what we try to do, having Apache Apex and Apache Geode.Use some of the advanced features and how it can integrate with the streaming technology like Apex. So that is what we're gonna see here in the next slide. So having a basic background of what Geode looks like and its capabilities, I'm just going to throw a light on some of the unique features of Geode, which is kind of very versatile and efficient. So one of the feature which Nitin did give overview on is the Geode's event notification framework. So Geode, despite being an large in-memory data grid, it also have a functionality to give a very event notification. Now what that means for an application is, suppose your data is large and every time you want to get updates from the data, instead of making and get or put call, which itself has its application latency, application can use event notification framework. So there are cache writers and cache listeners. So what cache listeners does work is in a kind of after event notification callback. So your application gets notified once there are events or tuples added to the memory grade or updated to the memory grade. Same as the cache writers, which kind of worked as a before event. So when the data or tuples to be go into a memory grid, so can be used for a kind of a data validation and cleansing. Then there are concept of async event listener, which is kind of pretty cool. So once data get inserted or updated into a memory grid, this async event listeners give capabilities to do asynchronous action post the data is changed or updated into the system. So this features and already having an functionality of fault tolerant and distributed memory grid can work in tandem with the streaming technology to work on certain features like designing a highly available distributed cache for a streaming application. All of this event notification framework, if the data is large, can be run on parallel or a serial. So serial, if this serial event notification will give a fairly less throughput, but will ensure that the data is notified to a client in the same order the way it is getting changed. But there are ways to get this notification in a parallel, so which gives a very high throughput data access to the client. And it can also be all of this data can conflated at the server level and get notified to the client. Another interesting feature from Geode is called continuous querying. So suppose you have a fairly large data set sitting across your data grid, and you are interested in a specific key set, which is maybe a very small portion of the overall data, which you don't want to make frequent scan queries across your data grid, but you just want to get notified only when that particular key sets or even queries. So the cool part is if your objects are stored in the memory grid, and you know that there are it's like the same way the query is highlighted here. You want to get notified when this query pattern matches any data entries which matches this query pattern. You get notified. So there's a feature called continuous query. What it does, you register a query, and all your gigabytes or terabytes of data, when this queries, any data updates or changes matches to this query are pushed to the client application, so that they just get those updates. So this is kind of a very cool feature which can integrate it with the processing framework like streaming technology. Also, like I mentioned, application can register for specific keys as well, so they get notified. So this is kind of a paradigm where you don't want to scan a large data set. You kind of freeze on a specific data which you are required on, send that data, register onto the server, and send that kind of register on the server, and you just get notified on that. So those were another cool feature. Now, how we managed to make use of these features and add certain functionality or improvements on Apache Apex. So I'm just going to talk about what integrations we did on Apex. So question, apart from data tolerant folks, out of the audience, how many guys are aware of Apex as a streaming technology? Okay, so there are a few. So I'm going to assume that people are aware of the Apex streaming technology, because that is kind of needed to understand this integration. So Apex in general is which provides a very scalable, highly efficient streaming technology where you can create a DAC to do real-time in-memory computation and processing. So Apex, this is what a typical Apex application in terms of DAG looks like, where you have an input stream, input operator which reads the data from the source, which could be a distributed file system, which could be a message queue like Kafka or some other place. It will have operators which is gonna filter and compute certain aggregation and pass it on to a different operator, which can choose to write it to different store. Now, one of the key feature of any streaming technology, and even Apex in particular, is to ensure the resiliency of the entire platform and ensure that platform is able to recover from the node failures. How that is obtained is using a functionality called checkpointing. So platform underneath, without user intervention, keep doing checkpointing at a periodic intervals. So what that means is, so Apex has a concept of windowing. So at a configured windows, Apex platform ensures that the state of the object of all operators get checkpointed at a state. So in case of any node failures, Apex platform will be able to restore that particular operator from the last previous checkpointed state, and to ensure that the DAC can recover from the node failures. Now, in the existing Apex application platform, this checkpointing, which is a very critical feature to ensure reliability, was done in HDFS. So what that means is periodically the object state gets stored into HDFS. Now, we all know that HDFS is a default tolerant distributed file system, which is a very proven technology for a large scale file system data access. But what what it is not good is writing small number of files or objects, because despite giving good fault tolerance, it has its own latency of writing the data in HDFS, because once that you issue a request to write the data, that data gets replicated across multiple nodes. So that feature kind of then becomes a bottleneck, because think about it, you have a DAG application which have hundreds of operators. Each operators, after every configurable seconds or milliseconds, writing its object state to HDFS. So if your HDFS writes are slow, or you have fairly large applications which are doing a lot of checkpointing, can in turn slow down the entire impact the performance and the latency of the application. So what we kind of propose now, since there are efficient and fault tolerant in-memory data grid like Geode, why not use Geode to checkpoint object state instead of HDFS to an in-memory technology. So previously the upper part, which looks like an in-memory layer, and the lower below is the distributed file system. What we have done is we changed the Apex platforms checkpointing, instead of doing into a file system, into a same in-memory layer into a Geode. What it will mean is for a larger application which have large number of operators, will give a much better latency, because the writing data into Geode, which is an in-memory cluster, has a much better latency than writing data into a distributed file system. And all of the entire platform now remains into an in-memory layer than going into a frequent file system IOS. So kind of you get rid of one of the disk accesses, which can potentially have impact on the overall application. So for this feature in the Apex open source community, we submitted a feature which can. So Apex already have a checkpointing storage agent, which kind of interfaces where user can write a different storage agent, which we write one for Geode, which does a checkpointing into a Geode cluster. We submitted the patch, and which is kind of merged into a or on the way in flight to merge into upcoming Apex releases. Another scenario to talk about the usual, now having this Apex Geode integration, which looks like this. One of the usual pattern what streaming application does is they read the data from some source, they do some filtration computation, and usually the pattern is to write the data in some NoSQL database, which is available for further analysis, or which can power your analytics dashboard or other stuff. Now, so what it means is usually streaming application end up writing data to another NoSQL databases. Now, this NoSQL databases, the kind of efficiency and the feature it's supposed restrict the features of the entire your application which you're trying to do. Now, let's assume you have a real-time application which is reading data, computing aggregates, and writing into HBase or distributed other distributed stores like MongoDB, which does not have features like transactions. So what we thought of, why not write a Geode operator? So Apex application should be able to write this data to an in-memory Geode cluster, which will give a much more higher write throughput just because it is purely in memory. So we then integrated a Geode output operator which can take different kind of data set. You can have a pure byte arrays or a complex POJO objects which get returned to a Geode cluster. Now how application benefits from this? So what are the benefits of writing this data into an in-memory Geode cluster, just more than a performance gain? So one of the cool things is Geode already have a pre-built query support. So now you have an application which reads, computes, and write to a Geode in terms of POJO. It is querying that data is fairly easy because Geode comes with the tools where you can query the complex nested object with the object query language, which is similar to SQL. You can query the nested objects, do a SQL-like queries if you have indexes on top of that. So that is one thing. Sorry?
There's a question on the webcast.
Sure.
What response times are you able to achieve on queries?
On Geode queries?
Yes.
So it's not Geode queries from Apex, or it's just Geode queries?
So the person who asked the question, could you qualify your question that it's Geode queries or Apex to Geode queries? I believe it's Geode because this was part of it first.
Okay, so so this kind of covers based on what Nitin has already talked about. So even despite being Geode span across multiple distributed nodes, for query mechanism, it's have a lot of efficiency. So first, your clients are already application aware. So you're querying for a particular data, it's already have a partition logic where I know where to find this specific data, which qualifies for this query. There is a concept of a single hop. So even if your data set is large and set across multiple nodes, it goes and finds as the qualifying node which is there and try to satisfy that query in one single shot. Also, there are yes.
So what is that node is in a different geographic place?
Okay, the different geographic?
Yes.
Okay, so usually people don't span one cluster across geographies. What they end up do is for stuff like disaster recovery, what Nitin already mentioned, what you will end up having is you will have one Geode cluster and a different Geode cluster in a different regions with this feature called WAN replication. Now, WAN replication is a built-in feature which ensures that at application level you don't need to do anything. You just configure, this is my London region, this is my LA region. So the platform ensures that both regions across WAN with the WAN replication should be in sync. So
yeah, so what is the response time for that, the latency? Depends on the WAN capacity?
Okay, so WAN replication, like I said, your normal queries never reference WAN. It is a feature for a disaster recovery. So that comes into a picture. If your entire region goes down, you have different, when the query gets routed to a different region, which in a concept of the cluster failures, and that definitely, that latency is impacted by because your query is now going across WAN to a different regions. Which for the initial question which I was giving in justification is the single hop, even despite being a large scale in-memory grid, with the single hop, the query qualification and finding the right node, it's able to fetch the queries in few milliseconds. So it's pure Geode does not have a scan-like feature. They do have indexes where you can run complex queries. They have function push down where you can, if you want to get a larger data, instead of getting all of data to a client, you can probably send your computation there on only the result set. But at a transactional level, all the data get to an application in a few milliseconds.
Another question. Apex is a native Yarn application. How does Geode interact with Yarn?
So basically, Geode doesn't interact with Yarn altogether. So same way Apex is kind of on top of Yarn, which uses Yarn's processing framework for a deployment and managing of Apex application. Geode is kind of a standalone cluster, so that can get deployed on a Yarn cluster or any bare-bones machine. So what Geode requires is you can configure, you can give it an ample amount of memory and spawn Geode cluster on any machine. And Geode already have some sophisticated deployment tools. So there are CLIs which can use to manage and deploy cluster. But in the shorter summary, it does not require Yarn. And if the question is about how they interact, Yarn, Apex running on Yarn, and all of these integrations, Apex will have an embedded Geode client. Let's say Apex as an output operator will have an embedded Geode client which will be interacting to a Geode cluster, which may be on the similar node, similar network, or the cross network. Okay, coming back. So that's kind of lost. So what I was explaining, so the benefits of writing this data in Geode store. So one is you're computing, you have your POJO, complex nested object, you're writing into a Geode, and you can just fire up the queries to the OQL queries to see your analytical results as the data being streamed. So Geode is meant for a fairly large number of clients. So it's not it's grew up being a transactional system, so it has the ability to handle large concurrent queries. So you can have a system which is streaming and writing and updating a fairly large amount of data. Same way you can have clients which can do analytical queries using OQL. Another benefit of writing streaming data to Geode is the visualization support. So Geode, if you guys are aware of an incubating project called Zeppelin, which gives a simplified visualization graphs and have a concept of a lot of interpreters too. So they have Spark, Flink, I guess a lot of other SQL interpreters to simply visualize. So, and they can get embedded. So the, Geode is already part of that. So again, use case to think about, you have a streaming data which gets ingested into a Geode. You can just fire up a Zeppelin visualization tool to see that how your data is streaming and getting updated in real time. Next benefit, another benefit which Nitin already covered, it has a sophisticated persistent mechanism. So you can choose to have data get persisted into a disk. You can choose to have your data get persisted into a distributed file system like HDFS. So, and despite that, data do get replicated across nodes. So the node failures, if there are node failures, the data from residing on the different nodes will serve the data queries. If the entire cluster goes down, the persisted, so that cluster or the region get recreated from the last persisted data. And Geode has a very good transactional support, which we will see in one of the integrations how we made use of.
Is it configurable, all this persistence?
All of these are configurable. So you can have a disk persistence, you can go to a finite level how much of where do you want it to flush the data? Do you want a persistent to be synchronous, asynchronous, many of those things. Okay. So this is so for this feature as Apex output operator to be able to write the data to Geode, we had submitted this feature to Apex community, which the pull request is accepted, and again it will be available in the upcoming Apex releases. Okay.
Can you go back one more?
Sure.
Thank you.
Okay, now there are these two features which we talked about, writing data to Geode and checkpointing, which is already there in the Apex community. There are other future integration which we are proposing and which to culminate it with integrated with Apex, which I'm just going to talk about. So, like I said, Geode has a very good transactional support. So how a streaming application can make use of this transactional support, because real-time streaming platforms and transactional system has never been used together. So there has always been two different parts, but how they integrating together can make use of to achieve exactly one semantics which is required in streaming application. So that is what there's one use case around that. Then how about all of the data, if your lot of data is already reside in Geode cluster, how can you do a real-time analysis on data? So there is an integration proposal is to write an input operator which can read the streaming data from Geode. Then one of the efficient thing is to these streaming application tend to have a reference lookup cache. So how about using a distributed cache operator in Apex? And then if your application also has supports a batch or batch queries, or suppose have a need to compute some complex analysis which cannot be done at application level. So for that, having a scan operator which will send the computation to servers and get that result, which can be used in streaming applications. So let's go over some of those. So transactional operators. So streaming technology usually comes with semantic model. There are usual data streaming technology or even ingestion pipelines tend to have the de facto 3 semantics of data flows. So there is at least one semantics where your data is ensured to get delivered at the destination with a fair amount of duplication in case of certain scenarios. Then there is at most one which nobody, I don't think, ever uses, because which can allude to a data loss. And then there is exactly one semantics which requires a lot of plumbing and integration with from input to processing to external system to achieve, because that's a difficult part to achieve in the large scale streaming technology, to achieve exactly one semantics. To achieve that, what it requires is a good amount of checkpointing, and where the data is written into that data store needs to have a transactional support, because you have a data which is being read from your input sources. They get aggregated, and the same window which gets snapshotted and goes to an external store. That external store needs to support transactional to achieve, and all of that wired together to achieve that exactly one semantics. Now, if your destination store does not have transactional support, it's very difficult or close to impossible to build an exactly one semantic pipeline in streaming. So that's why what we're proposing is to have a transactional operator which will write the data in Geode in a transaction fashion, because Geode already support transactions. So that's yes.
So when you said you write the data into the external source and it has to have the transactional feature, right? So what if that external source is a community hardware, it doesn't have anything?
It doesn't?
It doesn't have that feature.
It's not in the hardware. It's your data store as an application needs to have it.
Right.
So if you're writing to a RDBMS system which comes with a transactional support, but if you're writing to a NoSQL database, let's say HBase, which in the vanilla version you do not get transactions, so that is good.
So you mean to say to the database?
Yes, database. Okay. So next feature integration with Apex Apex streaming processing framework is an input operator. Now use cases, a lot of data which could be a raw data or a pre-computed data already resides in Geode, and a streaming application need to source this data. So all of my data which is already reside in Geode, I want to do a streaming analytics, or maybe I have already running DAG. I want to also make use of the data which resides in Geode cluster. So the proposed idea here is to have a Geode input operator which will utilize Geode's event notification framework to. So Geode has an event notification framework where client can subscribe that, hey, every time there is a new entry added, push it on to me. Every time there is update. So have an input operator which will use event notification framework, which get notified every time there is a new entry or new tuples added into a Geode data store, and pass it on to a real-time streaming pipeline. So that's the use case and integration that we proposed for streaming Geode data in Apex. Next is the cache. So any distributed application tend to have a references lookup. So it could be some ID to value mappings, and in a real scenario, no matter what plain simple application has, there are always some static data an application needs to have. Same is the case of streaming applications. What I've seen is how these caches are being maintained in the real-time streaming is all the computation nodes or operators, they integrate with the external system, maybe an RDBMS, maybe S3 or file system, where all the static data, which don't get updated so frequently, maybe once in 20 minutes or a half an hour. They go and query this data, maintain it into their local collection, and use it as a refresh ID lookup cache. Now, one of the hardest problem in the computer science as well is to efficiently invalidate the cache, because how you're going to tune your application is go and query and check if that data has changed, my static data has changed, or there is any update. So there are some caveats to that. So now you're gonna either poll for that data source every configurable amount of time. Now, to build a highly available and distributed cache operator, what we have again thought of is to use Geode's event notification framework. So you have a Geode distributed cache operator in Apex, which will give this update. So application does not have to go and poll for any data from the external source. If the data gets changed, application will get notified, hey, this particular key has changed or this particular key has been removed. So invalidate your cache synchronously, so you don't have to, your polling cycles are reduced. So that's one of the feature integrations which we are proposing, where we building an Apex operator which will use this notification and key registry features to power a distributed cache operator. Sure.
So this Apex and Geode, you mean to say it is very good for the structured data? Sorry, structured data, right? I mean, what if it is a non-structured data?
Yeah, it is. So Geode is a key value pair. So all of these features, even if let's say your data is not structured and what you're storing is images and a blob,
right.
What all of this feature is works on your key. So your keys get notified. So even if you're storing a blob and what you register this interest, not, let's say you do not have a structure where you can formulate these queries, but you do get notifies on your queries where these data sets are updated or added. So it can, the good thing is it works at both levels. If you have a structured data, it will work efficiently because you should be able to write queries like this. But let's say if you do not have a structured data, you'll still be able to use those queries based on your keys. Your keys changes, updated, you're still going to get those notifications.
But it has to be on a transactional database for the appropriate performance, right? For the external data source.
Need not be. So here in a particular.
So I can use any NoSQL database too in that case.
No, this particular feature, continuous query, is part of Geode.
Okay.
So your data is, so I assume your data is residing in Geode, and then you should be able to use this continuous queries to get this data, and then make certain integrations like managing a cache operator. Okay. And next integration, okay.
So, two things. One, you're talking about using Geode to speed up applications. Did you benchmark any sort of real application, real data set to see how much of an actual speed up do you get from that?
So we did a couple of integrations. What we did, so one of the speed up boost which you'll see in order of magnitudes, and which I think does not even require any proof points, is look at the checkpointing use case where your data gets checkpointed into a distributed file system. So it is straight away a big difference than writing into a distributed file system than writing into an in-memory layer.
So I understand the advantage, but did you actually benchmark? Here's the real application.
Yes.
With real data, with checkpointing. Here's how long it took with Geode. Here's how long it took.
Yes.
With
Yes.
And what were the results?
So by just replacing the HDFS-based checkpointing, having an application which have operators which are configured with exactly one semantics, which keep doing checkpointing. So we had it running on HDFS and we had it running on this Geode cluster with the in-memory checkpointing. We saw a micro benchmark that the checkpointing period has a better latency, and the checkpointing is 2 to 2.5 times faster than the HDFS-based checkpointing.
And how much does that account for the total application time? Did the application itself speed up by 100x? 2%?
No. So that so for a checkpointing it may not, because that depends on is your application is actually getting hurt because of checkpointing. So let's say you have a fairly small application and which does not incur a lot of checkpointing. So
did you check with any sort of real application with real data to see any particular application that actually uses that, and what was the result?
yes, so it's very straightforward. So you have a smaller application where object states are very smaller. So then your checkpointing into HDFS or into a memory is not going to give you a performance boost. So here is one of the data point which I can give, because I was at PubMatic. We were managing a large scale application. So their application DAG was fairly large. I guess, I don't know if it's right to quote, was one of the biggest enterprise deployments, but it was one of the initial large scale Apex deployments, which was taking an overall processing operator nodes used to spawn across 150 nodes, and cumulative memory size of the DAG was more than 2 TB. When we moved from so we had a migration project where we moved from AWS to on-prem. AWS HDFS cluster gives a faster latency because there all of your HDFS is made up of SSDs. When we move to on-prem where your HDFS is made up of disk, we started getting a performance downgrade because of the checkpointing. Because what happened there, we had a fairly large application with large number of partitions, and that was a time when actually we have gone through those cycles. So we for the first time we had to go and sit down and see that how many of our operators actually require stateful and statefulness. That was all because the checkpointing was hurting the application. At times it becomes so severe that let's say your HDFS writes are very slow and you have a large application with large partitions. It eventually really slows down your entire application. It to that extent that it starts building a lineage on your buffer servers, and it eventually used to lead to crashes as well. So that was a case study which we had seen that at PubMatic we had to go through all the process of.
And did you change to use Geode and use
No. It was when I was at PubMatic. It was like more than 6 months back.
So was there any application where you actually changed to use Geode? And
Yes, that's what I said. So there is a machine data demo. There are applications which are fairly large, and which gets when you create large partition, it get bugged. So that is where we saw the performance gain to 2 to 2.5 times. Okay, thanks. Yes.
So when you say you are in that AWS, they
Yes.
were using the SSDs. So would you say that the performance of the checkpoint is proportion to the RPM of the disk array, or this?
Yes. So see, it's when you're doing checkpointing in HDFS. So HDFS read and write latency is configured by how are you making your HDFS? You're making your HDFS is out of JBOD, out of SSD. So obviously SSDs are much more faster than a JBOD. So obviously, so there your HDFS write latencies were faster.
Right.
Okay. So how am I doing on the time? So this is anyway a last integration. So what it talks about is you have a streaming pipeline and you want to you have a small piece of analytics need to be done now, which you don't need to do frequently at a seconds level, and that analytics piece needs to run on all the data in the in-memory data grid. Now, one of the things which an application needs to do is to, I have like 2 TB of data which resides in my in-memory data grid. I have to get all of that data to client and run those aggregation or whatever my user-defined function is. So Geode already had a function where, same like MapReduce, you can ship your computation to a data itself. So Geode node not only acts as a data store, they acts as a computation as well. So you have that small piece of UDF which goes to a Geode server, gets run there, and the results get combined and sent back to the application. Now using that feature with some sort of scan operator. So having a scan operator which you configure with that application logic, which periodically pushes that computation to a data grid and just gives the result set. Then so using that application pattern we are proposing to have a Geode scan operator, which will have a predefined computation go to a server and the result state gets streamed into an application. So that's what pretty much it, all the integrations. So some of them are already there, which will be out for you to use and evaluate in Apex and Geode, and some of them are in flight, which is being worked upon.
Our next speaker is Suhas. So Suhas is a Hadoop veteran, and he co-founded Apache Ambari, and I think almost all of you are familiar with Ambari. He's also held architect roles at Yahoo, Pivotal, and Hortonworks. He was the chief architect of Pivotal Hadoop distribution, and was architect of Hadoop installation management and monitoring products at Hortonworks. And he's going to speak about an end-to-end Adtech pipeline from Kafka to Geode on Apex.
Thanks for the introduction. So today actually I'm going to be a demo guy. So I'm going to show a demo where the whole Adtech pipeline, streaming pipeline that we have simulated to do the streaming analytics on the various ad campaigns and advertisement metrics through data torrent Apex, and storing that data inside AMPool. So now as I'm going to show you some demo about the AMPool, I'm just going to talk a little bit about the AMPool, what the AMPool platform is, and so that would actually get you some more context that way. So you guys, heard about the Geode. So Apache Geode is basically the in-memory distributed in-memory grid. So we actually it's not changing here. I think I changed it over here. So but my screen is shared already, right? Screen. Okay. So AMPool is also an in-memory store powered by Apache Geode. So Apache Geode, you know, that has a lot of good functions, and primarily the data set abstraction that we have in Apache Geode is a key value store, right? So we have a distributed key value store for fast lookups or low latency transactional applications. But we are in AMPool, we are enhancing it to really support the analytics type of workload. So many times, people have a problem that they actually want to ingest the data very fast into memory, and the data should be really quickly available for analytics. So for many streaming analytics or batch analytics workloads that if we have seen, that typically data comes in hourly batches, right? And it takes a lot of time to really load that data back into the analytics system. So if you can really analyze that data right when it gets ingested into the memory, right? That's where the real power of Ampool would help you in doing the fast data analytics. So what we actually add on top of Geode, we actually add basically a table store. So we actually have a data structure, it's a table abstraction that we support in the memory stores, where you can actually store the rows with multiple columns. This is, again, as I mentioned, this is for high throughput analytics sort of applications in memory. We are actually also supporting the smart data tiering. That today we have basically the SSDs, RAM. We are going to have non-volatile RAM. These are the hierarchy, and then we have a disk. So how do you actually address this hierarchy of storage? We are having support for that. We also have a catalog where lots of our table abstraction, we call it as an M tables. So all these M table catalogs actually we also support inside the Ampool, where we keep the metadata about tables so that we can access them efficiently. We have a security, as well as we have a shell. That way you can actually go and access these table metadata, view them on the client CLI side, using the command line.
What do you mean by native interface there?
So native interfaces is essentially, you want to
Sure. Okay.
take
Java API is our default API for connecting with other stores that have been written using Java, such as SDFS, HBase, Hive, ORC, etc., etc. However, all the new non-volatile memory technologies that are coming out, the first version of the interfaces that are going to come out are going to be in C, and these are the native interfaces. So in addition to Geode, which does not have the native interfaces, we basically added native interfaces in the sense that we can actually, let's say, pmem.io or the new the new mnemonic project that is coming out of Intel. So we will be able to interact with those. So the time that all these non-volatile memory becomes sort of commonplace in commodity hardware, we should be able to utilize that. Yeah.
Now in Ampool actually we have this in-memory store, but that is backed by multiple pluggable store manager. That means you can have HBase, you can have HDFS as your persistent data store underneath. So we are agnostic to what sort of underlying persistent storage that we want to use. Also, actually on the north side, the interface wise, you can actually run the Hive queries without changing anything. You can actually have the Spark or MapReduce jobs that can run without any changes. Your application logic can run, and that can actually use the data from the in-memory Ampool's mtable store. So we have the north side interface where people can use their existing tools, as well as for persistence layer we can use the pluggable storage layer, whichever people currently using. So here are some high level bullets about what the value we are bringing in addition to Geode through Ampool. So I'm going to show you a demo where, as I mentioned, that we actually are simulated the complete advertising technology pipeline, where we have essentially said we have typically in advertising technology, what you have lots of users. You have basically the content publishers, and you have the advertisers who actually have lots of ads or campaigns that they run on the publishing websites, right? So typically, I mean, the users, content, and ads, they have some sort of an interest, and typically what these publishers or the ad exchange does is to essentially match the user's interest with the specific ad interest, and whenever user goes and sees a particular content, actually the specific matching ad is essentially shown. So we have tried to simulate all that stuff. So typically in this Adtech pipeline scenario, I mean, all these events, like user goes to a website, downloads a content page, get to see the ad, is essentially comes as a set of events which typically are called ad server logs, right? And those are essentially analyzed to find out which ads are doing better, which campaigns are doing better, how much revenue they are making, and so on, because each ad view or ad click or ad conversion event actually has some dollar amount associated with it, right? Also, there are bunch of updates typically happen not as fast, but typically happens to users interest or users profile changes. The content profile, sometimes content actually in fact changes, or even ad keywords or ad interest also, I mean, changes. So those events also we actually take into this pipeline and try to actually show you how the streaming analytics works. Oops. Around this. So as I mentioned, we have this ad server logs, as well as we have an updates to users, contents, as well as the advertisements themselves. All they basically come inside a Kafka. So we have a Kafka cluster. From the Kafka, actually Apex picks up all those events, and Apex basically stores those events into Ampool M table. But at the same time, Apex also basically does the streaming analytics on it by computing the top 10 advertisements based on the advertisement views by the users, or top 10 campaigns based on the clicks, the top 10 clicking campaigns stuff, and then essentially the data gets stored into HDB. This is a very high level view. We also are basically showing the visualization through data torrent. Now Apex to Ampool, again probably it's the next slide would give us the better and then we essentially visualize the data or ad metrics or campaign metrics through data torrent dashboard for the various involved parties.
Excuse me. What is the use case, particular use case for this analytics? Use case. I mean,
Use case is, this is advertising application or advertising platform, as I mentioned, where you have your website and you are basically publishing the contents, you are accepting the advertisements from the advertisers, and then on the background you need a lot of analytics or sometimes the streaming analytics to understand how your ads are doing. I mean, advertisers are giving you the ads, but they also want to see, I mean, how much I'm spending in real time, how many users are really coming and seeing my ads, how many of those are viewing my ads versus clicking on them. So all that analytics in real time is what we are actually showing you in this specific use case.
Makes sense. Thank you.
And for that, we are actually using the Ampool as an in-memory store for actually streaming the data and storing in our M table abstraction. At the same time, while actually doing the streaming analytics, while processing these ad events, we are also doing the lookups, very quick lookups to our in-memory store to augment certain data that is coming through ad server log events. So these are the typical things that streaming analytics require to annotate the data, right? So this is where you have ad server logs, you have a content ads or users updates, they are coming into essentially Kafka, and then in Apex context, let me actually just, so this box is where you have these Apex operators. Now the add server log is actually basically processed through Apex set of operators, and we are going to see the complete DAG soon. And then it basically computes the top 10 campaigns which are viewed and top 10 ads which are viewed or clicked, and then essentially that stuff is stored back into the in-memory store. So you can see the in streaming, actually all that latency is very applications are very sensitive to latency, so all that storage happening to the M table is, and this thing is very latency sensitive. So, and then it basically gets back and visualized through data torrent dashboard. Essentially these operators in Apex directly are storing the data into M tables for essentially the what we do is we store these users, ads and content inside the AMP pool, and we run the batch analytics on top of it. As the data is coming through streaming and getting stored in AMP pool tables, we also run the batch processing so that we can find the best ad that matches the specific user's interest, right? Because users' interests are changing, content is changing, ads keywords are changing, so we are doing the batch analytics to really find out for any given user what is the best matching ad to serve, and then we essentially generate this basically content to add and user to add mapping table, and this information is essentially used in our simulator or data generator to really pick up an ad for when particular user is randomly chosen for showing an ad. So you can see the whole closed loop over here, and all that requires an in-memory store accesses that helps you actually drive the pipeline a lot faster. So this is where I would end the slides, and I'll just show you now the demo. So I have the Hadoop cluster, HDFS, Yarn and Kafka installed through Ambari. I have a single node cluster on Amazon where we have these things installed through Ambari. I have installed, actually we also have a support installation of AMPpool through Ambari. In this case I haven't done that, but we support that. On that single node also I have installed the data torrent as well as the AMPpool. So I have this data torrent application ad stream. So I'm just launching this application. So what is the data torrent or Apex application? Is basically it's a DAG of operators which pick up the data from Kafka topics and processes and output that into M tables. Whenever during the streaming processing it requires any accesses to the data which is already stored in any memory store, it basically makes the fast lookups. So my application is essentially launched on the data torrent platform, single node data torrent platform, and this is hosted on this Amazon machine. So we can go and quickly check. Oops, I think this is failed. So we have some glitch here that we need to actually start it at least 3 times. So this is a real demo. Okay, so now you can see that first attempt failed, the second attempt is accepted, it is failed, and by magic now I'll show you that the third attempt must.
3-time charm, right?
Yeah. So.
It's Jeff Bezos. It's not a dog, it's a genie.
Now you can see here. So what it is doing is essentially it has a bunch of operators. So data torrent actually uses its streaming application uses the yarn to basically launch the bunch of containers, and each container actually runs a particular operator, and then operator basically some of them are the source operators, some of them are processing, and some of them are sort of sync operators. So source operators essentially read the data from Kafka, the processing operators process them in a streaming fashion, and the storage operators store them into Ampool. So if you see, there are basically 18 containers have been launched. Right now there is no data flowing, and if you see, this is the DAG of operators. So we have this 1, 2, 3, 4 and 5 operators which are reading the data from Kafka topics. Now out of this, four top two and the bottom two actually are sending them to the storage output operators, which are mout adds, content, server log, and this thing, which these operators, storage operators, are nothing but just streaming the data into Ampool, because we actually run the Hive query on that streaming data. I mean, streaming in the sense in a batches or hourly batches, we actually run the batch analytics. So we just stream and store that data into Ampool. Now we also read the add server log. This is another operator which passes the add server log events to add server stream counter. So that stream counter nothing but basically just finds out how many for a given ad or for a given campaign and a given type of event, how many actually events happen. So it just counts them. So events are either clicked events or view events or conversion events. That means whenever ad was shown, it was just viewed. Ad was shown, it was actually clicked. So those events we just want to count per ad and campaign. So that's where, and then basically it sends out those things separately to add top 10 counter and campaign top 10 counters, which computes the top 10 counters in a given specific window. So we have about 20 seconds worth of window, and then essentially those those top 10s are also basically stored back into Ampool for visualization. I mean, right now we don't visualize the data off of Ampool, because we actually have in data torrent we actually have a visualization support. So out of this thing, so these snapshot server and the result operators, they actually can directly feed over the WebSocket, directly feed the data to actually the dashboard. So we are currently using that. So you can see these are the various operators and these are the various containers, and they are essentially in active state. There are lots of other cool things on this dashboard. So what I'm going to do now is very quickly I'm going to start my data generation program. So this is Adtech stream generator. So as I said, we actually have simulated. We first populate the bunch of users, a bunch of content pages and bunch of advertisements, and then we actually generate the ad server log, which is nothing but a given user ID, this content ID was shown and this particular ad was displayed, and then event was like clicked or viewed. So we randomly generate this ad server log. Also we randomly generate some updates to the user's interest. So we keep on changing the interest of users. So you can see a bunch of users, contents, ads have been added, and now you can actually see the events have started getting published to the Kafka topic. These events are actually the ad server log events, as well as some of the events are marked as a UCA update. That means user content or ads updates. Those are typically less frequent, where ad server log events are more frequent. So here now you can see actually that it basically the whole pipeline started running, and so many events have been actually emitted and these things have been processed. The latency is right now high because initially we dumped a lot of data. So as the pipeline catches, the latency should reduce down. So now we can actually see, for example, top 10 campaigns So we have basically the data for various e-commerce consumer products, and we just taken those product itself, their information about the product itself as an ad information, and now you can see after certain interval of 20 seconds the top 10 campaigns are changing. So here it basically shows which are the top 3, because in that window only these 3 campaigns have been shown. Now in this window 4 campaigns have been showed, and typically each campaign there are so many 3 events. Toshiba's 3 events have been occurred. That means 3 ads were shown under Toshiba's campaign, and then they were clicked actually. So you can see actually this is running with taking on the real-time ad server log content and showing you how the things change. If you want to see the latency, actually
it is just a simulation, right?
It's a simulation, yes. It's still a single node system.
Data generation is essentially acting as a proxy for an ad server log. The rest is all real.
Yeah.
The rest is all real.
Yeah, I mean the actual data is just we have simulated, because we don't have actually the real website and ad exchange kind of data. So we are just simulating that, but all that events are actually flowing through this Apex pipeline. They are making the real-time lookup. So for example, in the ad server log you only have the IDs, ad ID, content ID and the user ID, but you need to actually during the real-time processing you need to get for that ad ID, tell me the ad platform, tell me the ad basically type, is it mobile ad or is it a web ad, and based on that you may want to aggregate the thing. So all that stuff is really happening with in-memory calls to Ampool. And
Around 10 events, a throughput of around 10 events per second with a latency of 20 milliseconds per event.
actually this is single node system which is running
even for
the
a single
whole
nodes, it seems.
No, the single node means actually the lot of
The generation is only also running on the node.
generation is also running on the same node, so there is a lot of load on the system. Latency is actually, I mean, because of it's a single node, actually it would help. But still there is a lot of processing going on, and the number of cores, if you see, are not that high actually.
So all the batch job you're running on Ampool, what that's the only aggregations?
Yeah, so actually the batch job is not shown over here. This is only the streaming analytics stuff is shown, but you can actually run the Hive query periodically every hour on the data that basically just we are storing the user content and this thing. Every hour we actually just take a snapshot of this data which is right there in memory, and we run the analytics and find out the best matching ad for a user, and then that we use by making a lookup this thing. Data generator basically takes into that stuff into account.
You said you're running Hive query. Are you writing it back to HDFS or something on this data?
No, it's still right. I mean, the Hive query is basically taking the data from Ampool and actually generating the mapping, user to ad mapping, and it's again storing that information back into Ampool. Because that's what we want to actually show the analytics use case for. The Geode, which only supports the key value store. We are now having the analytics the table store abstraction, which can be used for fast analytics right there.
But if you're running the Hive query, I was thinking you need to write the data on the HDFS so that you can run it, right?
Hive actually, no, I mean you don't need to write the data to HDFS.
Okay, it's in-memory data on that.
Yeah, so what we actually have is Hive actually you can actually just change the serializer, deserializers, and the storage, storage formats, storage handlers, so that you can actually just write it into any store that you want. So we have written that for Hive. So Hive logic doesn't have to change. It's just that you configure Hive to write the data into Ampool and read it from Ampool.
Okay, got it.
So,
thank you.
any more questions?
Any questions?
Hi, I have a question. At this point, you have only one use case, or you are in the process of developing another use case?
So we actually have, this is one use case we have. We are actually doing some of the POCs with our customers and prospects. There we actually have some other use cases as well. So we are working directly.
So do you have a use case on IoT or something like
Sure. So we are working exactly on one of the use cases where they are actually developing the IoT application. So
Thank you.
So primarily, I mean, we want to show that the same memory store can be very efficiently used for analyzing the data as soon as it lands into memory, as well as you can actually look up and do the transactional operations on that data as well. So combining that both the benefits together. Thank you.
So there's a question on the webinar. Is the dashboard CQ from mtable? Continuous query from mtable?
Yes. No, the dashboard doesn't right now actually views the data from mtable. Dashboard actually currently takes the data in real time from Apex operators, but you can actually as well visualize the data from mtable directly using any visualization tools.
So it's after the Geode plus scan operator is done. That's after that it will be.
Yeah. So we can write another operator which can just basically visualize or pull the data from mtable and push it onto the dashboard. So.
Any other questions?
Cool. Thank you.
So I wanted to thank the three speakers for increasing our knowledge and understanding of Geode and Apex with their wonderful talks. I also wanted to thank everyone who's here, people who joined us remotely on the webinar, and everyone who worked behind the scenes to make this meetup possible. And just a quick reminder, on your way out, do fill up the feedback forms that are on the bench behind you, and then hand it over at the entrance and get a t-shirt. Thank you.